So our project is the mobile LIDAR scanner for Senior Design 1. My name is Terry Fearn.
My name is Halterman.
My name is Harley Ketring.
My name is Gage Thompson, and our advisor is Dr. Liang Chang.
Project overview. So our project is the mobile LIDAR scanner. So we're going to be interfacing a microcontroller, specifically an Arduino, with a LIDAR scanner and an RC vehicle. Basically, we want to remote control a vehicle that has a scanner on it and be able to send it into an environment and take a 3D model of it. So our goal is to remotely generate 3D model of an environment, like I said, and we want to allow measurement and analysis of the saved environment. So it's not live. You'll have a file afterwards that you can look at and take measurements from at any time. This would have applications for the military, for interior design, for surveying, and for construction. So our team, we are all double E's.
I'm Harley, and I'll be going over the background information we gathered for the marketing requirements. So some initial considerations within our team were going towards accuracy, reliability, cost, and ease of use as our main considerations. We then gave a survey out to random people and found what they thought was most important. We found that functionality, specifically the accuracy, was the most important. Same with durability or the construction of the robot. The cost was the third most important. And lastly was just ease of use or ease of file size transfer. So we then used these requirements to determine what our engineering requirements would be. That way we could focus on that during the design phase.
Elijah here. I will be going over the engineering requirements. As Harvey said, based off of the marketing requirements and the survey that we ran amongst the different groups of people, we found that the most important aspect of the project was the detail and rate of scanning. So the detail is the resolution at which the scan captures the environment. The scan rate is how fast it'll scan the environment. So those two kind of work in tandem with each other to produce the scan. Excuse me. The cost of the robot, as talked about in class, should not exceed $300. The scanner weight should not be cumbersome, should not exceed over 10 pounds. If it was over 10 pounds, obviously it would be very annoying to carry around and do the scanning. It should have a combined battery life of at least 1 hour, so it doesn't die on you mid-scan. And it should be able to withstand hazardous conditions with an IP rating of IP57, guaranteeing resistance to light, rain, and moisture.
So for our house of quality, our marketing requirements were cost, durability, ease of use, and upload time. And for our engineering requirements, we required that our costs be less than or equal to $300, our weight be less than 10 pounds. We required our lifespan to be more than 1 hour of operating time. And for the number of controls, we wanted it to be easy enough for a child to control it. For the file, we wanted the upload time to be less than 1 hour. And for the upload quality, we wanted more than a 10 kilohertz scan rate, and that'll give you a very clear image of the environment in your file. Now, if you look at our house of quality, the arrows represent correlations. So the more arrows, the higher the correlation. And if the arrows go up, it's a positive. If the arrows go down, it's negative. So basically the main thing you can see is that the better we make our device, the higher it will cost, unfortunately. So we just have to work to maximize cost and also performance.
So starting with our design, we created a fan diagram. We used this to help us figure out, based on our marketing, engineering requirements, and house of quality, what all our robot will entail component-wise. So we started with the base levels of just the LIDAR scanner, the wireless control, and the microcontroller, and got more and more in depth from there, going into what type of communication it'll use, what type of antenna, even down to the motor control, what type of voltages it would be used. From there, we started weighing our component options. You can see an example on the slide here of some scanner options and how we scored them. We gave each scanner a rating based on how much it cost, what the range on it was, the resolution, and what type of software support it had. and we total those scores up. And we would do this for every single component in our project, but the component with the highest score between our choices would be what we would use for our project.
All right, I'm Gage Thompson. I'm going to talk a little bit about the level 0 and level 1 content for our project. So starting off with level 0, on the left, we can see a function table that goes into great detail about the inputs, outputs, and functionality of our mobile LiDAR scanner. And on the right is sort of a high-level overview of the inputs and outputs of the system as well. So the user controls a wireless controller, which interfaces with the mobile LiDAR scanner, and a 7.4-volt battery powers the entire system. And the output is a 3D model of the scanned environment as talked about before in an STL format. And then the level 1 content here, this is just a more in-depth look at the system. So the wireless controller and the battery are the same here, but the wireless controller interfaces with a wireless receiver on the remote controlled car device. And then that interfaces with the motor controllers, and the motor controllers provide voltage to the electric motors, which will cause the vehicle to move. And the battery is used to power the microcontroller, the Arduino that we talked about a little bit earlier. And the microcontroller will interface with the LiDAR scanner. It'll send data telling it what data to collect, and then it'll receive the data back from the LiDAR scanner and convert that into an STL file.
Right, Elijah here again. I'm going to be talking about the Gantt chart. This isn't the full Gantt chart. I just included a little snapshot, including the whole thing would have been a few too many slides we would have liked to talk about. But on the left, we can see our different milestones, including their categories, who they were assigned to, the progress, the start date, and how many days it took. So I separated it into Senior Design 1, which most of the tasks there have already been completed, as you can see by the progress being 100%. All the data on the left side of the Gantt chart will correspond to kind of a calendar on the right side. So you can see how many days it took. You can see if it was, on track, if it's a low risk, medium risk, or high risk item. Like I said, most of the items from Senior Design 1 have been already completed. Besides the deliverable 3 in our group presentations, those were in progress at the time of making the Gantt chart. For Senior Design 2, we included procurement tab, implementation tab, testing tab, integration tab, and evaluation tab. So I kind of thought all of those would intertwine with each other, so I had them all lasting around the same date. As we get our product and all of our devices from procurement, implementation will begin, and from there, as we create our product, we will continue testing and so on. Yep.
So this image here is an example of our end goal. So with LiDAR, you have a bunch of different ways you can pair it with algorithms to change the functionality of it. So for example, you have SLAM LiDAR, which is simultaneous location and mapping. And then you also have Hector mapping, and there's a bunch of other ones. So SLAM basically allows the LiDAR scanner to map where itself is in relation to its environment, whereas normal LiDAR just takes a scan of the environment. And Hector mapping is the example here where it can actually generate the entire landscape of the environment that you're in while also doing some type of SLAM mapping. This was actually from a study. So that is it. Thank you for your time.